Welcome to This is a Talk About Nothing. That's me, I'm Samathy Barratt. There are contact links at the top of the slides up there. If you want to use those, feel free. This talk was meant for 60 minutes. I've got less time than that, so some of it might feel a little bit rushed, but I am about all day and at PubConf, so feel free to ask me questions if you are curious, interested, have anything else you'd like to say about nothing. Is that slide blank? No? Yes? There's giggles. I think nobody's really sure. Cool. That's a good start to this talk, I think, really. Think about this sort of thing. This is the meme that sort of encouraged me to write something about this topic. I was already thinking about it anyway, but then I saw this and I was like, I should definitely do a proper talk on this subject. We got a toilet roll which is empty, but there's still one in the holder, and we've got a holder that doesn't have anything in it. That's zero versus null, apparently, maybe, or is it? Going to try and answer that. I think I disagree with this, but we'll see. So we're going to try and answer some questions in this talk. What is nothing? We're going to try and answer how do we represent nothing in computer science? We're going to have a look at is nothing equal to zero? When is it equal to zero? When is it not equal to zero? Is it sometimes equal to zero? And why do programming languages have so many different ways to represent the concept of nothing across all different programming languages in several different paradigms of programming, actually? So, starting off, zeros and ones. Zeros and ones are how computers represent everything. It's very basic computer science. Zeros or ones, highs or lows, ons or offs. A zero, in this context, in computing, classical computing, not quantum computing, a zero is zero electrical charge, or at least very little electrical charge. A zero is zero electrical charge, which is like nothing, right? If you've got no electrical charge, you've got nothing. However, a zero is a valid register value. So in your CPU, you have many registers, and any of those can have zeros in, and that's valid. That is valid information in those registers. Zero is a valid memory value, as well as being a valid register value. So you can have bits of memory, maybe your system RAM, which has zeros in it. Zero is a valid memory address, sometimes, depending on the system that you're on, and the language that you're using. But you can say, I want to address the 0th byte of my memory. Again, depending on what platforms you're on. So zero is data. It's interesting. It means something. But zero is useful data. We use zeros in the concept of representing various different things. Integers, floating points, characters. We use zeros for padding things to fill the space that we have. We use zero as termination markers and other sort of flags. And we use zeros in Boolean values as well to represent the concept of false. False is important in this talk, I think, because false is an interesting value. It's not nothing. So essentially, zero has a meaning. And while in historical lower-level computing, we've used zero to represent the concept of nothing, we can't just use zeros nowadays, because we want to represent much more complex computational, computer science things, and we can't just use zeros to say it's nothing. So zero is not nothing. It's interesting, it's meaningful, it has a purpose. So how do we represent nothing without using zeros? How do we represent nothing in programming languages without using zeros? I'm going to run through some categories in this talk. And we're going to start off with the category of zeros, and where we use zeros in programming languages to represent nothing. And then I'm going to talk about objects and how we might use objects in object-oriented languages to represent the concept of nothing. I'm also going to talk about other literals. I'll explain what a literal is later. I'm going to talk a bit about optional types. And I'm going to talk a bit about some nullable types. And finally, I'm going to talk about some other interesting nothings in programming languages and computer science. So we mentioned already that we can't really use 0 to represent empty or nothing, because 0 is useful information. And this is before the concept of objects, but we had languages like assembly languages. And we had languages like C and other things from around that sort of era, very early computing, where perhaps we did use 0 to represent nothing. I'm going to start off with C. I'm going to start off talking about null. So in C, we can initialize variables. Variables must have a type. So we've got two integers here. They're just straight integers. One of them is defined in the global scope, and the other one is defined inside the scope of the function main. The problem with initialization in C is the default initialization. If we define a variable in the global scope up there with the variable named Tycho, that receives default initialization. For an integer, the default value for that integer is 0. That makes sense. Okay, you define a new variable, you want it to contain a sensible value, and you start off at the bottom. And you call it, put a 0 in it, that's fine. However, if you define your variable series inside the scope of main, that is indeterminately initialized. So it just contains some garbage, basically. It doesn't contain an integer. It doesn't contain, well, it contains things, but it's just garbage. C doesn't really guarantee that that integer is going to contain anything sensible. It doesn't say it will contain a 0. It doesn't say it will contain anything. It might contain, I don't know, some water. Like, who knows, right? It's indeterminately initialized, so it will contain just some garbage because we haven't given it a value to initialize it. Now that garbage that's in that variable, is it nothing because it's meaningless? Is it nothing because it's not 0? But it is. It's an integer value, right? But it's meaningless to us because it's garbage. So is it nothing? I'm not going to answer that question. I'm just going to leave it. Pointers are also interesting in C. So a pointer in C is essentially a reference to a piece of a memory address, a section of memory. Now in C, we can allocate some memory with the malloc function up there. So we're allocating 10 characters, and we are creating the variable eros, which is a pointer to those 10 characters. After we've allocated the memory, we're going to immediately tell the memory management system that we'd like to free that memory, that we no longer need it, chuck it away, use it for something else. What's in eros now? Is it nothing? Is it a 0? Does it contain a character? Well, it just contains some garbage, actually. Is that nothing? Does that pointer to a character contain nothing? Or does it just contain data that we don't care about? Is that nothing? it's not a 0. Again, I'm not going to answer that question. I'm just going to leave it out there. So continuing on with pointer initialization, what we can do when we initialize variables is we can assign data to them immediately. And what we usually do when we initialize pointers and we create a pointer variable is we assign it to null. We assign null to it. Now you notice here that I've initialized 2 character pointers. One of them I've assigned 0 to it, which is not a character. And the other one I've assigned null to it. See, the thing is with C is that null is also 0. And 0 is just null, depending on the context. So 0 is an integer, but only if it's an integer in the context that you're using it. If you're assigning 0 to a pointer, then it's a special, super special, really important value that means that that pointer doesn't point to anything. But it definitely does, right? It points to an address which is 0. It doesn't point to nothing, it's an address which is 0. Now what's particularly interesting about this is that C does not have a concept of nothing. It just uses zeros and indeterminate values and the, things containing garbage, rubbish, that you shouldn't care about, but it doesn't provide any functionality to go, hey, programmer, this contains garbage, don't use it, it's nothing. C will just go, okay, yes, you can have an integer that you haven't initialized, and that integer is by default, apparently today at 3 o'clock in the afternoon on a Wednesday, points to the value 2,473. But tomorrow it'll be a different value. And so C does not have a concept of nothing. Actually, I'm going to give you some quotes from the K&R-C. This is quotes from my copy of K&R-C from the 1970s. It's pre-American National Standard C. So C guarantees that no pointer that validly points at data will contain 0. And they also say that we write null, however, to indicate more clearly that this is a special value for a pointer. And finally, in general, integers cannot be assigned to pointers. 0 is a special case. You'll notice that there's a really important word up there. We write null. There's nothing stopping you not writing the word null at all. You could write anything you wanted, as long as it's an integer. C will quite happily let you assign integers to pointers, even though it says you can't do that. Because it allows you to use 0 as a special case. And because it allows you to use 0 as a special case, it allows everything else. So this is the downside to using 0 as a representation for nothing. Is 0 is not nothing, it's an integer value. And it's an important integer value. But in the concept of C, in context of a pointer, it doesn't mean anything, which is fine as long as you have the context. If you don't have the context, it becomes a really big problem. So in C, in short, C is the same as null, which is not great. I'm moving on a little bit. I'm going to talk about objects. And I'm sure a lot of you have programmed in languages that use objects. It's very popular. Maybe some of you have come across the null object pattern. I don't think a lot of people will have done because, in my personal opinion, it is not a very sensible pattern. But it might be useful, and it's a thing that exists. So the null object pattern is an object which has no value or neutral behavior. And what that means is the null object pattern is where you use an object which represents null when a reference to an object would be nothing. So null, when a reference points to an object but it doesn't point to anything, Instead, it points to a null object. But the object that it points to, that's representing null, should implement all the interfaces that you expect for the type that the pointer is. And it should have no side effects when those interfaces are used. So essentially, you are allowed to have references of a type pointing to a null object of that type that has all the interfaces you expect, but none of the interfaces do anything, and there's no way for you to tell. Which is sometimes useful, but as I said, sounds like it hides a lot of errors, right? So here's an example. So I'm sorry, code is really hard to fit on a slide and make it big. So we've got two classes up here. We've got, on the left-hand side, we've got the class nonship, and on the right-hand side, we've got the class Anubis. The class Anubis has a number of methods. It's got a name that returns a string. It's got an affiliation, which returns a string. And it's got the launch method, which does a thing. On the other side, we've got a nonship, which has a name that returns a string that's empty. It has an affiliation, which returns a string that's empty. And it has a launch method, which does absolutely nothing. It's parse. It's a no-op in Python. And then in the middle here, we have a function which gets a ship and returns a new object of that type. So you pass it in a string, and it will return the object of the type that string is. So there's a bit of things going on in Python to convert strings into class names that I haven't put on the slide, but hopefully it makes a bit of sense. So what we do at the bottom here with the fleet variable is we are creating a list of objects, and we want to get a ship. We want to get two ships, one of the type Anubis and one of the type Rocinante. However, we've only got a class Anubis. We don't have a Rocinante. And so instead of returning a sensible ship object that is the Rocinante, or throwing an exception because it doesn't exist, instead our function returns nonship, which is a ship object, which pretends to be a ship, except it doesn't do anything. But what this allows us to do is it allows us to cover up the fact that that object is not available. And it allows the program to continue running without error, without exceptions, flawlessly functioning as if the ship Rocinante does exist, because we can perform all the operations we would on a regular ship on this none object. So like I said, it covers up all the errors that might happen. It doesn't throw any exceptions, but I'm not convinced that's a good thing. Okay, so let's talk about some languages that use objects. I'm going to start with Smalltalk, so a very early object-oriented language from the 70s. It was standardized in the 90s. But yeah, in Smalltalk, everything is an object. And Smalltalk has this thing that we might consider slightly weird nowadays, where instead of calling methods on an object, you send it a message, and it will respond to that message, which we don't tend to think about object-oriented programming with those ideas nowadays, but apparently in the 70s, that was what object-oriented programming was sort of originally thought about as. So, Smalltalk has a keyword, nil, which is a singleton object of type undefined object. Now, a singleton, there is only one object of that. There's only one nil in any Smalltalk program. There's just one. So every possible reference is a reference to the nil object until you set it to something else. And you can check to see if your reference, to see if your object is a nil object with this fancy syntax here, which is essentially we have a function and we pass it our object. But messages and weird syntax from the 70s. So it's not quite implementing the null object pattern because nil can throw if you send them a message that they don't define. So it's not a nil object pattern thing, but you can quite easily make objects that conform to the null object pattern because you can inherit from undefined object. So yeah, singleton object, which represents a null reference, a reference to nothing. But it's a reference to something because it's a reference to a nil object. But the nil object is empty. I'm going to talk about Python. Python is very similar to Smalltalk. It also has a singleton object, which is its own type. It's of none type, and it has the literal none. So it's just a keyword. You write none, and it refers to that singleton value, that singleton object. In general, Python's behavior is similar to Smalltalk. Any reference can be a reference to none. And you can compare whether things are none with the is keyword. So here we define a reference called Mars. We set it to none. We say if Mars is none, if it is the none object, because there's only one, so both of them can be none, we print a thing. And then we look at the type. The type of none is a none type. So again, Python does not implement the null object pattern. If you call methods on the none object that it doesn't define, it will throw exceptions. But you can inherit from none type, so do with that if you want to use the null object pattern. What's next? Oh yeah. So I want to talk a bit about casting. The reason I want to talk about casting goes back to what I was discussing earlier with the C programming language, where you've got null, which is an integer. In object-oriented languages, you can sometimes cast objects to pretend to be other objects. In Python, you can't really do that. You can cast a none object, a reference that contains none, to strings and booleans, but you can't cast it to types that don't really make sense, like integers, dictionaries, or lists. Now, you can't cast it to an integer because none represents nothing. If we cast it to an integer, what would we do? Because an integer must contain a value between 0 and max integer. Nothing is not an integer, right? Nothing is nothing. And so casting it to an integer wouldn't make any sense. That would be a bit silly. Casting it to a string sort of makes sense. Like if it just returned the empty string, I feel like that would make a bit more sense. But casting it to a string that contains the word none, it probably doesn't cause that much harm, and if it does, then you've probably got some problems going on in your program. Casting it to dictionaries, which are key value types, that doesn't make sense, because what would you do? Is nothing a key? Is it a value? Is it a pair of values? Do you return the empty dictionary? The exception it throws is actually it's not an iterable type, so you can't turn it into a dictionary. And that's the same exception that you get when you try to cast it to a list, which is just an array. It's not an iterable type, so you can't cast it to a list. A Boolean, however, apparently Python decides that nothing is equal to false, which is interesting to me because, well, like, false is just 0, right? It's the 0 out of 1 and 0. But we can't cast it to an integer. So why can we, and if we cast a bool to an integer, we get a 0. So you're telling me that nothing, is equal to false, but not equal to 0, because that wouldn't make sense. All right, let's talk about Ruby now. Ruby is also very similar to Python and Smalltalk. It's an object-oriented language. It has a keyword nil, which represents the singleton. Nil object can be assigned to any reference. Ruby has some nice fancy syntax that allows us to compare, to test whether a reference is nil. We have the .nil question mark. So if it's nil, print the string. I think that's really cool. I think that's quite nice. You don't have to do the is none or is nil function or anything like that. You've just got a little couple of extra characters, some pretty syntactic sugar. We've also got the and dot operator, which again I think is really fancy. So the and dot operator means if the reference Doniger is not nil, call the method moving, which is really cool, or the property, if it's a value. If the reference Doniger is nil, don't do anything, just ignore that whole statement. And I think that's really nice. It means that you can just carry on without throwing exceptions. If your reference is nil, we don't care, that's fine, just continue. What does that sound like? It sounds a bit like the null object pattern. So Ruby doesn't actually implement the null object pattern because you still have to use this operator explicitly. You can't just call methods on nil objects. But it somewhat implements the null object pattern. I'm going to talk about casting the nil object in Ruby. And this is particularly fun because Ruby defines casts for most of the built-in types from the nil object. So you can cast it to an integer, and Ruby says it's a 0. You can also cast it to a string, but Ruby says it's an empty string, which makes quite a lot of sense, really. But you can cast it to an array as well, which Ruby says it's an empty array. And again, with Booleans, it's a false, which would make sense, because it's a 0, right? So there's a few differences between some various languages with object-oriented programming. Those are the main ones that use objects to represent nothing. And they all behave roughly the same, sort of similarly, with some good gotchas to catch you out when you switch between them. And now we're going to talk about literals. I mentioned some literals earlier and what a literal might be. So a literal is a fixed string, usually a keyword, which represents a value in the language that we're using. So I said, none represents the none object singleton, nil represents the nil object singleton. But any symbol for a fixed value is a literal. So true, false, null pointer, that's from C++, 1, even the characters that you write in your strings. They don't represent the character, like they represent the ASCII value for the character or the Unicode value for the character, so they're a literal. You could write a programming language that takes all numbers, they input, right? So you write source code with 1, 2, 3, 4, and it goes, yes, the one literal in this programming language is equal to 10. Right, so they just represent values. You could make them represent any value. Cool. C#. C# is the first language we're going to talk about with literals. It has a null literal. The null literal represents a reference type variable, which currently doesn't hold a reference. So it's consistent with our object-oriented languages, except null here is not an object, but it is the null reference. So it's not an object. So you've got a reference to an object which currently contains something that isn't an object. It just represents nothing. So a bit of a stark difference from our object-oriented programming languages. Null is not an object, and we can't do object-y things with it, like call methods, because it don't have any. So here's the example up here. Yep, we've got a class. We define a variable with the type of that class. We assign null to it, and then we can assign a new object to that variable later on. So you can assign that null literal, you can use that null literal to make any reference null. And this is quite funny. So D is my favorite programming language. I really enjoy using D. It also has a literal called null. And the code looks like that. It's exactly the same as C#. How fun is that one? I think that's really, really quite amusing, actually. However, the semantics are a little bit different, which is obviously perfect. Catches you out if you switch between the two, which probably nobody does. So the snippet is exactly the same. However, C#'s null hasn't got a type, I don't think, not a C# programmer. But D's null is the type of null, even though it's not an object. It's not a, it's a fun one. So D's object is a type of null, and there are some explicit casts that you can do to cast it to other built-in types. So as well as setting it to reference values, pointers, you can also make integers contain null, and then they contain 0. And you can cast it to strings as well, and it gets the empty string. But it's important to note here that these are explicit casts. So if you try to assign int I equals null, D will complain at you and go, this is not an integer, you can't do that. Which makes sense, right? Okay, so I'm now going to talk about C++. I like C++, it's quite good. It's not as good as D, but here we go. C++ is really fun. It's got templates and, good things like std null pointer t. So in C++, the nullptr keyword is a literal of type stud null pointer t. And that's important because that type is available to you as the programmer. So the null pointer literal is an empty class. It's not itself a pointer type or a pointer to anything type, but it's an empty class. And your access to the stud null pointer t type is really useful when it comes to specializing functions. Now, for those of you who haven't programmed in a language that supports function overloads, what we've got here is we've got 3 functions that take different arguments, but all the functions are all called f. And what happens is when you call function f, if you pass in an integer, C++ will go, aha, I know which function you want. You want the function with the argument integer. In this case, we're using pointers, right? So if I call function f and pass in an integer pointer, as we've got on the right-hand side here, it will call the first function, which takes an integer pointer. Great, cool. If I pass in a double pointer, C++ will go, aha, yes, I know what you mean. You want me to call the function f that takes a double pointer. Cool, great, I can do that. That's nice. However, if I pass in null pointer, so the reference to null, that could mean if I've got a variable that contains null pointer or is of type null pointer and various things, if I pass that in and I didn't have this f at the bottom, which takes a null pointer t, C++ would go, yeah, but null pointer could be an integer or a double. I don't know what you mean. Help, I am confused. But because we've got access to this stud null pointer t type, it means that we can use null pointers and we can pass them in, and C++ will be like, cool, okay, I know what that is. I will call this function at the bottom for you. This is very useful in templates, which are big, scary things that if you don't program in C++ will forever be terrifying. But yeah, so stud null pointer t is interesting in this field. It's different to everything else, really, because you have access to that type and you can define functions that take those types. C++'s null pointer can be implicitly converted to any other pointer type. That makes sense. Any pointer can be a null pointer. Cool. And you can try and explicitly cast it, but your compiler will probably complain at you unless you turn it off. So essentially what this boils down to at the bottom here is if I try to cast a null pointer to an integer, that's like saying, hey, I want you to take this 64-bit integer and try to fit it into 32 bits. The compiler will go, no, no, that's bad, do not do that. Likewise with a character. It will go, hey, that's only 8 bits. No, you can't do that. However, if we've got a long that is 64 bits, the compiler will be like, okay, good, yes, I can put a memory address into an integer for you. I can do that for you. So, like, don't do these things. Don't try and cast null pointer to a long. That's silly. You should be using a pointer. But you can, and I think it's interesting because null pointer represents nothing, and you can't turn it into integers or characters, but you can turn it into particularly long integers. Like, if it's not a thing, how can you convert it into a long? Anyway, so, right, Java. What slide am I on? Cool. Java is very simple in this particular space. Java's got a null literal, which is of null type. You can assign the null literal, the keyword null, to any reference variable at any time. It's not possible to create variables of null type, and you can't use null type like you can in C++. So you can't cast it, and yeah, you can't declare variables of null type. So cool, all right, it's just got a literal that is the null reference, and you can't use it for anything other than the null reference. I'm going to talk about JavaScript. I think JavaScript is a little bit full of dragons. And one of my friends said to me earlier today, JavaScript likes you to be able to continue whatever you're doing as much as possible, even if that means you end up with strings that contain the string undefined. That sounds a bit like the null object pattern, actually. JavaScript, null is a primitive value. It's not, this is from the documentation on Mozilla's website. Primitives are data which is not an object and has no methods. However, for compatibility reasons, if you do type of null, it will tell you it's an object, because JavaScript. It is a primitive value which has a literal, the literal null. You can assign it to anything. But yeah, there's a single instance of it, but it's not an object, it's a value. But as I said, casting, doing funky things with null in JavaScript, you'll end up with JavaScript going, ah, yes, this is an integer now because you said it is, or this is now a string that just says undefined, and that sort of thing. If you have any stories about that, I kind of want to hear them. I'm not a JavaScript programmer, so don't really know these things. I want to talk about optionals with a bit of, okay, yeah. So I've just talked about null references, as in references to objects, and references as in pointers to things. But these are nothings in the concept of we have a thing that says, hey, there's a thing over here, except there's nothing over here. But now I also want to talk about optionals, and optionals are a bit different. Optional types is normally instantiated with a type. So this is C++. I'm using it for the example because I can write it. So at the top, we've got a function called affiliation, which takes an std string and returns a stud optional, which contains a string. So the optional will encapsulate either a stud string or nothing. But what's important about optionals is that it's a detectable nothing. And it doesn't contain the empty string, it doesn't contain a null pointer, it doesn't contain anything like that. It contains something you can go, is this nothing? And it will tell you it's nothing, not a string. So the example here that we're using, we've got a function called affiliation. We pass it a string. If the string matches Sally Ride or Doniger, return the string mcrn. If we pass it the string Navu, then we return those two curly brackets. The prints at the bottom, std count, because is that how you say it? Not really sure. Never really pronounced it out loud. C out, I suppose. Console out, yeah. So the console outs, the first one, we pass it Sally Ride, and we return from our function mcrn. And that line prints mcrn, and it prints mcrn because that's the optional value, and that's the value contained in the optional type. However, the second line, the optional type will be nothing. It won't contain anything. So instead, when we call value or, we end up printing the string OPA. So, yeah. Whoop. Let's just go back a sec. Yeah, so I may contain data, I may not, essentially. It's an actual detectable nothing value. It's not nothing, it's not a null reference, it doesn't have a thing in it, and it's really interesting, right? It's completely separate from all the other nothings that we've talked about. So optionals came from functional programming languages, but they're probably available in a language near you. We've got them in Scala, Haskell, Swift, C++, Python, Rust, Java, basically everything. I mean, that's not a list of everything, right? But so, right, I apparently haven't got much time left. I've got some slides to flick through. So I'm going to briefly flick through the Rust optional and move on to nullable types. So Rust doesn't allow references to be null. The only way you have to say that something does not contain a value is with an optional type. I think that's really cool. We use in Rust, we've got the matching syntax here. So if your optional type does not contain a value, you have to use match. It's a bit different to C++'s kind of value or syntax. But essentially, it's the same thing. But yeah, the curious thing about Rust is that it's the only way you can represent the concept of nothing is with an optional type. Scala also has optionals. C++, I showed you that. Nullable types. Sort of like optionals. The most popular one you will have heard of is SQL. So here we've got an example where I create a table with 2 columns. I put a record into that column with the values Miller and null. And you will recognize that the second column, alive, is a Boolean. Booleans can only contain true or false, right? Apart from when they're null in SQL. So that's a nullable type. It's got a distinct value that is not one of its regular values. It's got a distinct nullable value, which is not true or false. And when we select records, we get empty. It doesn't return an empty string. It doesn't cast it and go, hey, this is false now. That's what you meant, right? It goes, no, you didn't put anything in there. It's null, it's empty, it's nothing. So when we select it, we can select records depending on whether they're null, fields, if they're null, and we can also select fields if they're false. And you'll note if we say, hey, we want a record with alive equals false, there's no records. Null is not false. It's a nullable type. So it's sort of like an optional, but this is built into a type system. C# has nullables. You can define them using fancy C# syntax, which I think this is really cool. I think that's a great idea. In a similar way, Boolean, Balta, contains null, and null is not true or false. And yet, there we go, with the little question mark at the end, it's suddenly a nullable type. And we can detect that with the has value. Other interesting nothings, I'm really trying to pick up the pace. Common Lisp. Common Lisp, this is fancy. It doesn't have a concept of nothing. Nothing is just an empty list, which is also nil, and nil is a literal keyword. Oh yeah, empty lists are also false. Nil is false. In fact, anything which doesn't contain a value is false. If it contains a value, it's true. So that's fun. Yeah, that's really weird. Concept of nothing is just if it doesn't have anything, containers that don't have anything in it are nothing, but they are because they're a container. The container exists, but there's nothing in it. You can't apply set theory to Lisp, right? Because a set is a set, even if it's an empty set. Scala's got some really fancy nothings. Scala's a JVM-based language with weird syntax again. So we've got the nothing type in Scala. Nothing is a subtype of every single other type in Scala, everyone, even the ones that you define. And you can create lists of nothing. And then you can make references that are of type list containing strings and assign them with list of nothings. It's a special type. Okay, I'm almost done, don't worry. Scala also has a nil literal, which is just the empty list, i.e. a list of nothings. And I'm going to skip quickly through to floating points. Floating points contain this fancy thing where if your floating point has a sign of 1 or 0, an exponent of all ones, and a fraction of ones or zeros, it's not a number anymore. Which is not really a nothing, but it's this special fancy value which basically says this is not valid. It's not a thing anymore. It's not what you expect it to be. And so I'm counting it as a nothing. Okay, so we covered some different languages, ways of representing nothing. There's a whole bunch on there. I wish I could talk to you about it. So to finish off, I've got 4 slides left. What is nothing? Well, nothing is always something because we can't represent nothing in computer science. So it always has to be something, but the thing that it is and what it means is contextual, right? If you've got zeros and you're assigning it to an integer, then that means something. But if you assign it to a pointer in C, then apparently that doesn't mean something, except it does. So it really only means something if you're looking at it and you care about what it is. But nothing is always something, and it's always something that you could be interested in. How do we represent nothing in computer science? Well, we've got objects, we've got values, we've got special objects, yeah, empty containers even, and special numbers. Is nothing equal to 0? Sometimes, but I hope not in modern computing. Whew. Okay, cool. That's it. I think I ran a little bit over time, but given that this was 60 minutes, fitted into less than 60 minutes. Hey, 48 minutes is fine. All right, thank you very much.